Hi everyone, I'm Kristin Lauter, and I'm thrilled to be here to help celebrate 40 years of elliptic curve cryptography. Elliptic curve cryptography is very much tied up with my own personal history, and so it's a pleasure to look back and reflect on the 40-year history. In fact, I was very pleased to be a co-organizer and a host for the 25-year anniversary of Elliptic Curve Cryptography Conference, which we co-hosted at Microsoft Research. And I'm very thankful to the steering committee for ECC and specifically to Tanya Lange and Stephen Galbraith for inviting me to give this talk. So elliptic curve cryptography played a very big part in my life because in 1999 I was hired to go to Microsoft Research to work on elliptic curve cryptography with Peter Montgomery. And in particular, Peter was a very close collaborator and colleague of mine for more than 10 years, and we focused intently on implementation of elliptic curve cryptography and commercial deployment. And it was finally deployed in 2005 in Windows Vista. So let me talk a little bit about that history. So Peter Montgomery is very well known for a number of things, but including he wrote the Big Num library, which was a multi-precision arithmetic library for Microsoft, which was used in our cryptography implementations. And he's well known also for Montgomery curves, y squared equals x cubed plus ax squared plus x. So curves of this form, one example of those is ECC 25519, which was introduced by Dan Bernstein in 2005. That curve is defined over a finite field FP, where P is 2 to the 255 minus 19. It's a pseudo-Mersenne prime, thus the name ECC 25519. And it's been widely deployed in many libraries and protocols using the Montgomery ladder. And Peter's also well known for efficient Montgomery multiplication. Now, the ECC 25519 was not being considered and deployed at that time in roughly 2000 to 2005 when I was working with Peter. And in fact, for those kind of pseudo-Mersenne primes, the reported ratio of the cost of inversion to multiplication was something like 80 to 1, because you could do very fast modular reduction with Mersenne or pseudo-Mersenne primes. Whereas Peter's implementation of the Montgomery multiplication and other fast inversion techniques that he had meant that at Microsoft Research, we had an implementation where the ratio of inversion to multiplication in the finite field for general primes was more like 5 to 1. So this actually indicated that it was a good idea to consider affine coordinates for elliptic curves instead of the typical weighted or weighted projective coordinates, because the weighted projective coordinate system gets away with no inversions for each elliptic curve operation, but at the cost of more multiplications. So actually, both for our elliptic curve implementation and later for our pairing implementation, pairing-based cryptography, we were able to use affine coordinates and use things like Peter's simultaneous inversion trick. And so we did a lot of work to both implement and improve, optimize the implementations for different architectures. In fact, for the not just for the Windows crypto API and the later the CNG, but also for the Windows CE, which was the embedded operating system at that time. So we wrote a number of papers, including papers with Kirsten Eisentrager, Mathieu Siet, Marc Joie, and Michael Nerig on all of these kinds of improvements for elliptic curves using affine coordinates. So it was an interesting experience working with all of the developers in the Windows Crypto API team, and we were very proud to eventually get this elliptic curve crypto shipped in Windows Vista. I think it was largely because of the Suite B algorithms that came through and necessitated, it made it a requirement to actually support ECC for crypto for any government contractor. So that was the main thing that really made a difference and allowed us to ship ECC in Windows. And once it was deployed in Windows, it was easy to get it spread both to other products such as the Windows CE operating system and throughout the industry. So the crypto API was replaced by the CNG, which was released in 2005. And on a personal note, that was a great experience for me to have worked for years to build up the relationships across the company with developers and a lot of different product divisions, and then to have the technology and our elliptic curve crypto libraries eventually shipped in product was in 2005 was very exciting. So as you can see, elliptic curve crypto in Windows Vista included support for signature algorithms such as ECDSA and also for the elliptic curve Diffie-Hellman. So these were largely based on the Suite B algorithms requirements, and the standard at that time. I don't quite remember exactly the curves, but there were prime curves, binary curves, and Koblitz curves. And in this initial version, I know that we supported prime curves and not so much the binary and Koblitz curves. There were various concerns, including issues of security. But so using the prime curves that were standardized, I think the ones that were standardized in the IEEE P1363 document were the ones that we used. And so then it was also interesting working with developers for the Windows CE operating system. It was an early version of ARM, and we had some optimizations and improvements which worked for the type of architecture that they were supporting at that time. Overall, it was a very interesting experience to be working on the early deployment of elliptic curve cryptography. I can barely remember it now, actually, but there was quite a bit of cooperation across the industry. I have a quote here from the Red Hat customer portal, actually, which showed using that later they had support for the curve 25519 that was added to OpenSSL. That reminded me that we worked with developers from OpenSSL, and also remember working with Bouncy Castle at the time. They were developing a cryptography library for .NET that supported ECC. And it was the Microsoft .NET framework that provided built-in support for ECC through those classes. So there was cooperation across the industry, companies including Certicom, where we were talking quite a bit about how to get elliptic curve cryptography deployed, and so it was eventually a great success to see it deployed widely and spread across the industry. So before moving on to the next part of my talk, where I'm going to move from talking about implementations of ECC to pairing-based cryptography, I just want to say that as a number theorist, it was also really fun to work on elliptic curve cryptography in that period because it raised a lot of other interesting questions, like, for example, generating curves over finite fields with prime order, which led me to work on complex multiplication for elliptic curves, and then actually complex multiplication for genus 2 curves as well, and higher dimensional abelian varieties. So it was a very fruitful area to work in for number theorists, including now starting to work on pairing-based cryptography. So you've heard a lot about pairing-based cryptography from Dan Bonnet's talk, and I'd like to just talk about a couple different applications of pairing-based cryptography that probably were not covered in his talk. So for one, so the BLS signatures, the elliptic curve-based BLS signatures, or Bonnet-Lin-Shaham signatures based on the VE pairing, or it could be one of the other pairings, like the Tate pairing, the 8 pairing, all these different optimizations of the essentially the VE pairing. But BLS signatures had a couple of really nice properties. So one was the fact that they were shorter. So that was one of the big motivations for adoption of BLS signatures. But a second aspect was that you compute the BLS signature and it's homomorphic in the sense that if you have 2 points on the elliptic curve and you take the pairing of the sum of those with some other point, that will be the same as in the target space, actually multiplying the pairing of each of those 2 points separately, taken with the third point. So that homomorphic property was important for applications, including we developed homomorphic signatures for network coding. So network coding was widely used for content distribution in peer-to-peer content distribution networks like BitTorrent. And the advantage of network coding, the way that peer-to-peer content distribution works is that many different peers will divide up some kind of like content, like a movie, to be distributed, and it'll be divided up into packets. But if each of the packets are just kind of sent randomly all around the network, then you can have a bottleneck waiting for kind of the last packet to arrive at any given peer. Whereas network coding, what it does is take a linear combination of all the different packets and spread those all around. So that's good for avoiding, kind of a bottleneck waiting for some particular piece of content. But the problem is it makes content pollution a lot easier because one, nefarious node, adversarial participant, can quickly spread garbage throughout the whole network by just polluting their linear combination of packets. So we needed some kind of measure to prevent this type of pollution attack, and the BLS signatures provided a really nice tool for this. So we can actually insist on packets to be valid. They need to have valid signatures, and the nice thing about the BLS signatures is that because they're homomorphic, they can be recombined, and they fit very well with the homomorphic property that is necessary for network coding. So this was written up here in this. You can find this in this Wikipedia article, and the original paper with Dennis Charles and Kamal Jain was appeared in the 40th anniversary annual conference on information sciences and systems. So this was an interesting application of the BLS signatures for peer-to-peer content distribution, and the interesting thing about this space was that the security relies on the hardness of inverting the Weil pairing. So that introduced kind of an interesting new hard problem into the space. So next I'd like to talk about another application, which is kind of interesting, probably not very well known. So the BLS signatures enabled a framework, a non-interactive zero-knowledge proof systems framework called the Groth-Sahai framework, which used pairing-based elliptic curve cryptos to enable, for example, anonymous credentials or privacy-preserving credentials, and then as an extension of that, also delegatable anonymous credentials. So Melissa Chase, who was a researcher in my group at Microsoft at the time, had worked on delegatable anonymous credentials, and we realized that this idea could be applied to enable privacy in the healthcare system in an interesting way. So I was working actually from starting around 2008 a lot on privacy in healthcare and interested in privacy of electronic medical records and encrypting medical data. But it was interesting to me that if we tried to keep the electronic medical records, private in the sense of the storage of people's private health data being encrypted, for example, or using things like later homomorphic encryption, there was still a problem that if you go to the doctor and you get some procedure and then the insurance company needs to be billed, they'll find out, what conditions you have and what procedure you have. And so I thought it would be much more compelling from a privacy standpoint if you could actually also protect your privacy from the insurance companies, because there's a lot of data available that you can see how much health data is aggregated and actually sold. And so I thought it would be nice to be able to protect the medical data kind of end to end. So the delegatable anonymous credentials can be applied in this setting because when you go to the doctor and they order some kinds of procedures or tests, so they need to get compensated for your visit, this can be enabled with a credential system, which is allows you to kind of delegate tokens to various other parties in the healthcare system so that they would be able to have valid tokens and the insurance company would be able to confirm that it should make the payments without knowing exactly what the procedures had been. So this was a paper with Melissa Chase that appeared in the Usenix 2010 HealthSec workshop, and it's also on ePrint. But of course, not very popular with the healthcare system and healthcare providers, of course, because in general they want to, collect this information. So it was never deployed that I know of, but it's an interesting and fun application. And it shows how elliptic curve cryptography can have a wide spread influence. So in the last part of my talk, I'd like to talk about the follow-up. With the advent of quantum computers and in the future when we have, full-scale quantum computers that are available, they will undermine the security of elliptic curve cryptography, to put it bluntly, to put it lightly. So the quantum threat is that there's polynomial time quantum algorithms for attacking elliptic curve crypto. And if M is the number of bits, so for example, like 256-bit ECC, if M equals 256, you can see that a quantum attack on ECC requires 360 m cubed time and 6 m qubits. And this is roughly according to the Prusalka estimates from 2004. In 2019, of a paper with Vore, Martin Rutler, and Michael Narig, with a little bit more precise estimates of the exact number of Toffoli gates and things like that that's required to attack elliptic curve crypto. But it confirms the asymptotic estimates from Prusalka. So you can see that with m equals 256, you're looking at needing roughly 1,500 qubits on a quantum computer. So even with in comparison with RSA, where m would be roughly 2048 for roughly the same security level, you can see that 2 times 2048, you would need a 4,000 bit quantum computer and 4,000 qubits. And so the interesting thing is that while for classical attacks, one of the reasons for the adoption of ECC is because we didn't have sub-exponential attacks, so we could get away with a smaller bit size. And that was good for, efficiency. What happens when you move into the quantum world is that that smaller bit size translates into a lower threshold in terms of how large of a quantum computer you need in order to attack ECC. So it's kind of interesting. It flips the vulnerability from making it, less vulnerable to more vulnerable at the recommended bit lengths. So once we have a full quantum computer at that size, the elliptic curve crypto systems will be broken, and so that's reflected somewhat in the timeline for recommendations from, for example, NIST and NSA. So the Suite B algorithms came out in 2005 and recommended the use of elliptic curve cryptography with those parameter settings that I showed earlier, roughly m equals 256 or 384. But in 2016, the CNSA requirements came out and increased the minimum bit length for ECC from 256 to 384 and advised that it was no longer required to implement them. So in response, that NIST started a 5-year quantum crypto competition from 2017 to 2022, and there are a number of different hard math problems that were used as the foundation for the systems that were proposed. So roughly speaking, code-based cryptography, multivariate cryptographic systems, lattice-based cryptography, and even supersingular isogeny graphs. So the code-based cryptography was introduced by McLeish in 1978, multivariate cryptosystems by Matsumoto and Mai in 88, Hofstein, Pfeiffer, and Silverman introduced the lattice-based crypto with the Entru company in 96, and with Dennis Charles and Eyal Goren, we introduced supersingular isogeny graphs in 2005. So that's the only elliptic curve-based system. And so I'm just going to focus the rest of my talk on the supersingular isogeny graphs and the hard problem that those are based on. So we actually introduced these supersingular isogeny graphs at the 2005 NIST hash function competition. And the hard problem was to find paths between nodes in the supersingular isogeny graph. This is actually a problem that had been studied by Stephen Galbraith in a paper from 1999 with only a kind of exponential algorithms known for solving this problem. So it seemed like a good foundation for a whole collection of new crypto systems that we now call isogeny-based cryptography. So the basic idea at the time was that we wanted to use graphs. So think of a graph G as being given by the vertices V and the edges E. And in particular, we wanted to use K regular graphs, so K edges coming out of each node, and the graphs should be undirected. So you can go either way on each edge, and also wanted to have kind of optimal expansion properties. So as you walk around the graph, you should quickly get to kind of a uniformly random place on the graph. And we also wanted, obviously, to have no known routing algorithms for finding paths, which was the underlying hard problem. So it was fun to find this set of slides that I actually gave at the ECC 2006 conference, introducing these graphs and this application of elliptic curves. So this is different than ECC because you're not doing the Diffie-Hellman problem on a single elliptic curve. Instead, the vertices of the graph, each vertex is an isomorphism class of supersingular elliptic curves, mod P, and the curves are going to be defined over either FP or FP squared and labeled by their J invariants. The vertices of the graph can also be identified or thought of as maximal orders in a quaternion algebra by looking at the endomorphism ring of the supersingular elliptic curve. We know from the Eichler class number formula that the number of vertices in the graph is roughly P over 12. So in our initial proposal for the cryptographic hash function, we proposed P to be roughly 2 to the 256, so that with square root attacks, you get something like 128 bits of security. So the nodes of the graph, again, are isomorphism classes, FP bar isomorphism classes of supersingular elliptic curves, and then the edges will be isogenies, and that's where the isogenies come in. So isogenies are birational maps, from one elliptic curve to the next, so they can connect the nodes in the graph. And they have the property, like in the separable case, so if the degree of the isogeny, the degree is the size of the kernel. So if L is usually taken to be the degree, L is often equal to 2. So as you can see, it's co-prime to the characteristic P, which is a very large prime. And so in that case, the isogenies are separable, and you can think of the isogeny as just being modding out by the kernel. And you get a L+1 regular graph, and the way that the hash function worked was that you can use an input to the hash function and divide it up into blocks. In this case, bit by bit, you could use it to walk around the graph with no backtracking. So no backtracking is allowed. So that was the hash function that we defined. It was written up in Science Magazine in 2008. So this is a picture of a graph with more than 200 nodes for a prime, which was somewhere around 2,500. And so it's just nice to have a picture of what you could also think of this as the Hecke graph. And it's got a lot of deep connections to number theory. So again, it was an example of working in elliptic curve cryptography, and the applications brought us to a lot of interesting questions in elliptic curve in number theory, actually, and including hardness of walking around on this graph of the supersingular isogeny graph. And we also worked on higher dimensional analogs in 2007, also with Charles and Goran, published an analogous paper on the graphs that you get from superspecial abelian surfaces. There's a lot of related work in this area, including working on these graphs with level structure, alternate protocols, for example, one popular one called Seaside, due to Tanya Lange and her collaborators. Lots of follow-up work. Sorry, this slide is a little outdated, but on signatures, attacks, graph structure, the ski sign by Christophe Petit and his co-authors, and many other different directions. So I'm glad to get a chance to talk about elliptic curve cryptography in all of its glory over the last 40 years. So both the implementations and the extensions. And thank you so much for listening.